So you'll remember that in the last subsection, we were talking about this case of blonde hair and blue eyes. Let's look a bit more carefully at that example now. So you'll remember that last time we said that 40% of people have blonde hair and 20% of people have blue eyes. And we said that if these were independent, if they had nothing to do with each other, then the number of people with both blonde hair and blue eyes would be 8%, 20% of 40%. But in fact, we see that 10% of people have both blonde hair and blue eyes. So this shows that in this case, they're not independent, because the probability of blonde hair and blue eyes isn't probability blonde hair times probability blue eyes. But the problem I'm interested in is here. If you know that someone has blonde hair, what then is the probability they have blue eyes, given they have blonde hair? So if we already know someone has blonde hair, then we know that they are in this section of the table. We know they're in the 40% of people with blonde hair. And of those 40%, 30% have brown eyes and 10% have blue eyes. So within that 40%, brown eyes are 3 times more likely than blue eyes, or there's a 3/4 chance of brown eyes and a 1/4 chance of blue eyes within that 40%. So in mathematics, the way we say this is the probability someone has blue eyes given that we know they have blonde hair. And we use a vertical line like this, where this vertical line means given or assuming that or conditional upon. So given they have blonde hair, we know that 1/4 of those people have blue eyes and 3/4 have brown eyes. So that answer is 1/4. If we think more carefully about what we're doing there, we're looking at all the people with blonde hair, and we're asking what proportion of those have blue eyes as well as their blonde hair. So if you think the way we did this calculation, it was probability of blue eyes and blonde hair over the probability of blonde hair. So in this case, this was 10% divided by 40% to get 1/4. And so this probability of given or assuming that or conditional upon is something we call conditional probability. It allows us to talk about the conditional probability of one event given another event. Like, what's the probability of the event happening given that we know some other event happens, or assuming that some other event happens? So let's see the formal definition of that. So the definition is that A and B be two events, and so the conditional probability of one of the events B given the event A, so this is the conditional probability of B given A, is what we said about blonde hair and blue eyes. So remember, the vertical line means given, and this is the probability of them both divided by the probability of the event we're conditioning on. And we don't want to have divide by zero problems, so we probably ought to say with probability of A greater than 0, so we don't get divide by zero problems. Typically in this course, I won't bother actually saying where the thing being conditioned on has probability non-zero. You should take that implicitly. And so this is the definition of conditional probability. It's the probability of both divided by the probability of the event we're conditioning on. And as we did with independence, there are kind of different ways we could use that. So in this formula, if we know probability A and B, and we know probability of A, then we can work out the probability of B given A. And that's what we did up here in the example. We knew the probability of blonde hair, 40%. We knew the probability of blue eyes and blonde hair, 10%. And thus we could work out the probability of blue eyes given blonde hair, 1/4. The other way we can use this is it helps to rewrite it slightly. We can write this as by multiplying the PA up. You can say the probability of A and B is the probability of A times the probability of P given A. And so if we know both of these, then we can calculate this. So we can calculate the intersection if we know the probability and the conditional probability. One more thing here, which is about tying together conditional probability and independence. If we suppose A and B are independent, then what can we say about the conditional probability? Well, the conditional probability of B given A is the probability of A and B over the probability of A. But if they're independent, we know that you get the and probability by multiplying the probabilities. So if they're independent, the top here is probability A times probability B. And then we see that the probability of A's here cancel. We just get probability of B. So if A and B are independent, then the probability of B given A is just the same as the probability of B. That is, we haven't changed the conditional probability by learning that A happens. And similarly, if we just swap the letters round, we'd also get the probability of A given B. Probability of A. So independent events don't change the conditional probability. So conditional probability is kind of useful for working out what happens in the case when we don't have independence. When we do have independence, we can just use the and probabilities, multiplying them together, and everything's nice and easy. But when we don't have independence, that's when we need to use conditional probability.